Hello grade 12s and welcome to this video, the first video on electrochemistry. Grade 12s, electrochemistry tends to be a very challenging topic because it brings together almost all of your knowledge in chemistry and from grade 10. So I do find that a lot of learners struggle with it, and based on that my advice is that you interact with the videos as much as possible, take down notes. If you have a question, write it down, send me a text message, email me. Ask me your question in class the next time you see me, because every single thing that you learn, every video that you watch will form the foundation of the next video. So it's important that we get your foundation right from the word go as soon as possible. In this video, I'm just going to introduce you to the two types of cells you will deal with this year, and I will do a bit of grade 11 revision. That's it. So to start off, you're going to be studying two different types of cells, the galvanic cell and the electrolytic cell. The galvanic cell can also be referred to as the voltaic cell. Inside your galvanic cell, we have spontaneous chemical reactions. What that basically means is that once you put your chemicals together, they will react on their own. These are all redox reactions. Remember, redox reactions involve the transfer of electrons or the change in oxidation numbers at the minimum. And basically what we are saying is that everything will happen on its own. We don't need to provide, for example, a battery or cell to complete the circuit and force the reaction to take place. The second thing that is important about a galvanic cell is that inside your galvanic cell, we have that chemical energy is converted to electrical energy. So this should remind you of something that you've been dealing with since grade 10, and that is the battery. Your normal battery, like a Duracell battery that you connect in your TV remote. Galvanic cells are, well, those cells that you find in your remote are a form of galvanic cells. We have chemicals inside of the cell or battery that will react on their own as soon as you connect them in a circuit. You don't need to drive the reaction drives itself and converts chemical energy into electrical energy. The second type of cell that we're going to be studying is the electrolytic cell. The difference, or one of the biggest differences between your galvanic cell and your electrolytic cell, is that inside of your electrolytic cell we have a non-spontaneous chemical reaction. That means that when you put all of your chemicals together, they will not react on their own. We need to force the reaction to take place. And the way that we do so is by providing electrical energy. So we provide the cell, we provide a battery, we provide some source of electrical power that will force a redox reaction to take place. So we say that inside of a galvanic cell we have electrical energy being converted into chemical energy. Now this might not make much sense because you are so used to galvanic cells, but your electrolytic cells are still called cells even though they don't produce or give off, or their main use is not to provide us with electricity, but instead to give us a useful reaction if we provide the electricity. It can be a bit confusing, but just take note of these differences. They will help you as you go along. So as mentioned, inside of these two cells we have oxidation and reduction reactions. This is grade 11 work that you need to remember. Firstly, oxidation is the loss of electrons. You may remember oil rig. This is a short way of remembering oxidation is loss. When we have an oxidation half reaction, some substance is losing electrons. The substance that loses its electrons is called the reducing agent. So we say the reducing agent is the substance that is oxidized. It is the reducing agent because it causes another substance to be reduced. Okay? If, for example, we have zinc in the presence of the copper ion, zinc will lose its electrons, copper will gain the electrons that zinc loses. Therefore, we say zinc has lost its electrons, but is causing copper to gain electrons and be reduced. Therefore, zinc is called the reducing agent. It has been oxidized, but is the reducing agent. That can be very confusing. For your reducing agent, the substance which is oxidized, when oxidation takes place, you will find that the oxidation number increases. So if we look at this reaction of zinc, where zinc is being oxidized, it is losing electrons and acting as the reducing agent. Zinc goes from having a charge of 0 to having a charge of positive 2. So we say that when something is oxidized, its oxidation number increases. And that's what you're seeing here. Very important when you're dealing with electrochemical cells, they contain what we call electrodes. And what you're going to find as a rule is that oxidation takes place at the anode. So how we remember this is we say anox. Okay, oxidation will always take place at the anode. Now let's take a look at reduction. Reduction is the gain of electrons. So back to oil rig, we have reduction is gain. The substance that is reduced is called the oxidizing agent because it gains electrons from another substance, and when it does so, the other substance is oxidized. So therefore, the substance that is reduced is the oxidizing agent. It is responsible for another substance being oxidized. When we look at the oxidation numbers, when something is reduced, we find that the oxidation number decreases. So here we are looking at copper. We start off with a copper ion with a charge of positive 2. It then gains 2 electrons and gets a charge of 0. So our oxidation number goes from positive 2 to 0. We say that there is a decrease in the oxidation number. We find that inside of our electrolytic cells, reduction takes place at the cathode. So how you're going to remember this is red cat. Reduction takes place at the cathode. So far, the things that you need to remember is oil rig, oxidation is loss, reduction is gain. You need to remember anox, oxidation takes place at the anode, and red cat, where we say reduction takes place at the cathode. Alright, now oxidation numbers. A lot of learners tend to think of oxidation numbers as charges, but if you look at reactions like this, these are redox reactions, but there are no ions taking place in these reactions. Everything is covalently bonded, and therefore we have a bit of a problem. If none of these are charged objects, then what is the oxidation number? Guys, an oxidation number basically shows how electron-rich an atom in some compound is. That's what it is. That's all that it is. You will find that in a lot of cases, your substances have the oxidation numbers of their ion charges. But oxidation numbers, even substances that are covalently bonded can have oxidation numbers, and they are a measure of how electron-rich these atoms are. So when they are bonded, how many electrons tend to be around them, or how closely are the electrons to them versus the substance or atom that they are bonded to. So I'd like to remind you of the rules for allocating oxidation numbers that you learned about in grade 11. There's many rules, and unfortunately the only thing you can do is learn them off by heart. There's not a lot of logic to it, just a whole lot of rules. So firstly, when you have a substance that is made up of one type of atom, or in other words, one element, then you are going to find that the oxidation number is 0. So helium, it floats around on its own, has an oxidation number of 0. Sodium is a metal, so if you have a block of sodium made up of a whole lot of NAs bonded to each other metallically, each atom has an oxidation number of 0. If you look at your diatomic substances like hydrogen, here each hydrogen atom has an oxidation number of 0. Something like S8, we have a whole lot of sulfur atoms that are bonded together, but we call this an element because it's one type of atom. So even there, the oxidation number of each sulfur atom is 0. So when you see only one type of substance, only one type of atom, note that the oxidation number is going to be 0. Rule number 2. For monatomic ions, we are going to find that, well, these atoms, these ions, are given the ion charge. So your group 1 metals have an oxidation number of positive 1. You may remember in grade 10 you learned +1, +2. Skip the transition metals, +3, plus or minus 4, -3, -2, -1. You learned about this in grade 10. So lithium, sodium, potassium, when they are bonded as ions, they're in group 1, which means they lose 1 electron. So they have charges of +1, but we also give them an oxidation number of +1. You group 2 metals such as beryllium, magnesium, and calcium. They lose 2 electrons, so they have a charge of +2, but we also give them the same oxidation number of +2. Your halogens are found in group 7, and they normally have oxidation numbers of -1. But there are exceptions to this rule, and the exceptions are when substances like chlorine, bromine, or iodine are bonded to fluorine or oxygen. Now, the reason why we have this exception is because both fluorine and oxygen have very high electronegativities. So if they are bonded to a substance that also wants to have a negative charge, then instead of that other substance having the negative charge, fluorine and oxygen, which have high electronegativities, a high tendency to pull electrons towards them, will have the negative charge instead. So a good example of this is iodine bonded to fluorine. Both iodine and fluorine are in group 7 of your periodic table. So technically they should both have a charge of -1 or even an oxidation number of -1. But since this is one substance, when you add oxidation numbers of a complete substance together, the oxidation number should be 0. So since fluorine is the more electronegative substance, we give it the -1, and as a result, your iodine is going to be +1. Okay, so just take note of these exceptions. The exceptions become easier when we say things like fluorine is always -1. That is a rule, study it, know it, because it's going to help you whenever we have, again, these exceptions. Hydrogen is usually +1 because, well, it's in group 1. But again, there are exceptions. When hydrogen is bonded to a metal like sodium, right? Sodium is in group 1. If hydrogen is bonded to sodium, we have ionic bonding. Sodium will get the charge of +1. Hydrogen, since it is more electronegative, will get the charge of -1. Okay, so hydrogen is normally +1, but when it is bonded to a metal, it will become negative because it is more electronegative than the metals. More rules. Oxygen is usually -2. But if you have oxygen bonded to hydrogen, like in peroxide, hydrogen peroxide, in this case, we are going to find that the oxygen gets a -1 while the hydrogen gets a +1. If oxygen is bonded to fluorine, since fluorine is so electronegative, fluorine will still maintain its -1, because remember we said fluorine is always -1. And oxygen, as a consequence, will have a charge of +2. So watch out for these exceptions. It's how we catch you out. Just remember, if you ever are looking at a substance, I mentioned that adding everything up, you should get 0, but this is actually just for neutral compounds. So when you have something that's covalently bonded or ions that balance out completely. If I give you, for example, a polyatomic ion, then the entire substance's oxidation numbers should add up to the ionic charge. All right. These are the rules. They can get very confusing, but the only way to learn them is to study them over and over again and to practice them. I don't believe that you should spend too much time on this because you are going to be making use of what we call the table of standard reduction potentials, which is going to make your life a lot easier. I'll be looking at that in the next video. But for now, I'd just like to remind you of, well, where you may need to use these oxidation numbers. We can say we have a substance like Fe bonded to PO4. And I will say to you, I want to know what the oxidation number of the phosphorus atom is. Now they've done this the long way, but I'm just going to stick to what they've done. We have Fe, the ion, in this case iron, bonded to PO4. PO4 is a polyatomic ion that is going to have a charge of 3-. How do I know that? Because we study it off by heart in grade 10. It's something that you are expected to know off by heart. So since this entire polyatomic ion has a charge of 3-, iron should have a charge of 3 positive. So now what we do is we say, remember right at the top we said if we have ions, so IONS, on their own, they get the oxidation number equivalent to their charges. We know that if we take the oxidation number of the iron plus the oxidation number of phosphorus plus the oxidation of 4 oxygens, we should end up with an oxidation number, well, a total, of 0. So we're now going to sub these values in. We have positive 3 plus, we're going to put X in the place of phosphorus because we are trying to find out its oxidation number. Plus, we have 4. Remember, oxygen normally has an oxidation number of -2. This is one of the rules, so we put in -2. Sum it up, it equals 4. Now we simply need to solve for X. We have X equals, this is -8, move it over, we have positive 8 minus 3, giving us positive 5. So that means in this substance, iron has an oxidation number of positive 3. Phosphorus has an oxidation number of positive 5, and each oxygen atom has an oxidation number of -2. The next example, so the answer here is positive 5. In the next example, we are looking at just a polyatomic ion. This polyatomic ion, you should know off by heart, and has a charge of -1. They want us to find out what the oxidation number of the manganese will be inside of the ion. So again, we have 1 manganese bonded to 4 oxygens. 4 oxygens, oxygen normally has an oxidation number of -2. And since this entire ion has a charge of -1, instead of adding it up to 0, we say it adds up to -1. We put in X in the place of manganese and solve for X, and we find that its oxidation number is positive 7. So these are examples where you may need to make use of these oxidation numbers. Oxidation numbers are also useful when we want to identify during a reaction which substance is reduced and which substance is oxidized. So these numbers are very important, but again grade 12, we are going to be making use of that table of standard reduction potential. So when you watch the next video, make sure to have your table with you.